I'm sorry to hear that. Could you please describe any issues or symptoms you're experiencing with product B? This will help us identify the problem and find a solution quicker.
Listen, I don't have time for this.
I understand your frustration. Let me connect you to a skilled human operator who can assist you further.
Hi everyone. We're living in highly disruptive times when it comes to testing the limits of LLM-driven applications. Personally, it feels like we've reached a stage where we can build AI agents that can fluently converse, leverage domain knowledge, and even adapt to our specific needs. But one significant question remains: can we enrich these agents with more advanced reasoning capabilities? Can this be done in a straightforward way? And will we be able to maintain predictability and control over the LLM's reasoning process? These are the questions we will be exploring in this video. And if you stick around, I promise you'll gain valuable insights as we delve into how advanced reasoning can be added to our agents. Throughout this process, we'll explore a prototype solution and a live demo. So stay focused and keep watching. Before we dive into design, let's clarify our use case. Let's assume that we're building a conversational customer service AI assistant. While the ability of the agent to converse with customers would be one of the very first tasks that we would focus on implementing, reality is that the agent must manage various other functions to remain effective. Some of them, like controlling conversation scope, need quick responses and can be handled with simple rules and LLM calls. However, others, such as providing accurate domain knowledge, self-correcting in real time, or deciding when to transfer a conversation to a human, demand deeper, more complex reasoning. For instance, determining when to escalate to a human operator requires the agent to analyze its own performance, assess user sentiment, and evaluate how well it can meet the user's needs. This kind of reasoning involves thorough examination of intention detection and other factors that may affect conversation effectiveness. Given the complexity of such reasoning process, we do not want to directly hard-code the execution plan for every problem that agent needs to tackle, as we would lose all the flexibility and autonomy we hope to obtain from agents. Instead, we want to define the problem declaratively and let the agent figure it out on its own. But how can this be done? For the agent to autonomously reason over complex tasks, it needs to be equipped with a generic reasoning capability. Such capability, shown on the slide in the form of orange boxes, can be then applied to a selected group of agent functions, enhancing them with more advanced reasoning and decision-making support. At this point, you may ask, aren't we already providing our agent with reasoning by using an LLM algorithm along with customized prompt? The answer is yes, but only to a certain degree and for simpler problems. In situations that require more granular and specialized decision making, we need more than just a single LLM to handle the task effectively. Ideally, we want to have greater control over how the process is performed, allowing for fine-tuning at a granular level. At the same time, we want it to remain flexible and autonomous so that our agent can manage it independently. How to approach this? The idea is very simple. If a single LLM is insufficient, we can follow a divide and conquer strategy and build a more advanced reasoner capable of breaking down a large reasoning problem into smaller sub-problems, which can then be distributed across multiple specialized agents and tackled independently. Basic prototype illustrating this concept is shown in the picture. It leverages the capabilities of large language models and multi-agent system design by first breaking down complex abstract tasks into smaller pieces using LLM meta-prompting. Each such subtask is then managed by an autonomous agent, allowing for focused problem solving. This framework operates like a dynamic workflow execution engine, granting a high degree of autonomy at every stage of the process. Furthermore, the modular design ensures that each agent can operate independently and in parallel while still contributing to the overall goal. This flexibility allows the system to adapt to different types of challenges and quickly respond to varying levels of complexity. For example, in situations when sub-problem needs further decomposition, the agent responsible for this subtask may further decompose it into smaller, more tractable from the reasoning point of view subproblems. Before we move on to the demo, Let's analyze how this prototype works. Once triggered by the incoming problem to solve, shown on the top of the picture, the reasoning module activates the planning agent, which encapsulates the abstract problem in the form of meta prompt that is then sent to the LLM algorithm. The meta prompt includes details such as the problem context, key variables, and desired outcomes. For example, inside the meta prompt, we instruct the LLM algorithm to plan step by step and to break the original problem into smaller, fine-grained subtasks. As a result, the meta prompt is not intended to generate a final output, but to create a resolution plan that breaks the problem into smaller components, each with instructions on how to address them. Here is an example plan produced by the LLM algorithm. In this plan, the problem has been broken down into 6 specific subproblems, each accompanied by defined instructions presented in the form of a prompt. With the entire problem broken down, the planning agent dynamically instantiates a group of sub-problem resolving agents, assigns to each of them their specific task, and triggers them to execute. These agents in turn call LLM algorithms to perform their local reasoning. The local reasoning results from all agents are then collected by the information fusion agent. Based on its own local instructions provided by the meta prompt, this agent uses the LLM algorithm to integrate all knowledge and make the final decision. The final outcome is then reported by the information fusion agent to the component that initiated the reasoning process, which in this case is the core AI agent's LLM algorithm. It is important to note that the presented reasoning framework is generic and can reason over various abstract problems, provided it is supplied with contextual knowledge describing the state of the problem. Agents are created dynamically and where possible execute tasks in parallel to accelerate decision making. For example, if we were to ask it to reason about self-correction, the meta prompt and its outputs would look like this, and they would then undergo the same decomposition and execution as in the earlier presented case. Let's now explore how we can apply our agentic reasoner framework to support the human handoff functionality of a conversational AI assistant. In this setup, the assistant's conversational capabilities are driven by its core LLM. Additionally, the assistant is equipped with a human handoff function that continuously monitors conversation with customers and evaluates the likelihood of needing to transfer the conversation to a human operator. The probability is sufficiently high, the assistant will recommend handing over the conversation to a more skilled human operator. Before running the full live demo, let us simulate a reasoning at a specific time during the conversation. Okay, so let's first have a look how the planning works in practice. We've got a code where first we've defined the main conversational LLM prompt, instructing the agent to be a customer care agent type. His goal is to resolve the problems that customers may report. There are 2 specific products. We explain that one of them suffers from a certain issue that can be resolved, and that the agent has to help the user in resolving the problem. So this is basically to give the system prompt to our main LLM driving the conversational AI agent. The next thing we have here is a certain simulation of the conversation. So we've just filled in the conversation where assistant and user are communicating with each other, and we will sort of use that snapshot to run it and in the background initiate the agentic reasoner tasked with identifying whether he should suggest our agent to hand off the conversation to a more skilled user. And of course, the probability of handing it over to a skilled person is based on the context and the way the user is communicating with our assistant. So just to be clear what we are simulating here, have a look at this conversation to understand what's the state of that conversation at the moment. So we've got the assistant that says hello, Next, user tells the assistant that he's got the problem with a service. The assistant asks the user what is the product he's having the problem with. The user first states that he doesn't know, he's confused and very upset about it. Assistant tries to mitigate the situation and responds, don't worry, let's try to figure it out. Can you tell me more? Which product you're having the problem with? And then the user responds, I think it's the product A. Great, can you explain what issues? Asks the assistant. And then the user responds, I'm unable to log on. And that's where we stop. So this is the actual conversation, and now we initiate our planner, we feed the planner with the current state of the conversation, and we will see what happens, what probability we will get out of that planner. So how do we do that? If you look over here, we've got a coordination agent, which is an agent built as a separate thread. So we will be running all the planning in parallel whenever possible. But we start with the coordination agent, and that agent is responsible for intercepting the user problem. So this is the, well, sorry, not the user problem, but intercepting the task it has to reason over. So here it is, identify if current conversation with the customer should be handed off to the human operator. That's what that agent has to figure it out. And what we are providing in addition to it is our conversation context, right? So that the agent can reason over using that data. And as you can see, I've created a method percept, because in agency theory, agents observe the environment and then act. So first thing to trigger that planning agent is to let him see that there's a new task. Okay, so let's now go into the coordination agent's percept method and see what's happening over there. So there it is. First thing we do is we put that new task onto the agent's queue. As I said, it's a multi-threaded multi-agent system prototype that I've built. So there are queues on which new tasks that are put, and then agent starts to process them, and it happens for any type of agent that we will be talking in this demo. So we put that task onto the queue, and once that task is being initialized by the agent, it invokes the act method. So it starts acting on the task. The details of that are hidden in the base class, so I don't want to bore you with all those things, but there is a run method. It's a thread, so inside the run method the agent inspects its queue, and if it identifies there's a new task to execute, it starts executing it, calling method act. So let's go back to that method and see what's happening here. So first thing we do is we generate the meta prompt. As I said before, the agent's responsibility is to create the meta prompt that it will use to initiate communication with LLM and get the plan for executing the task that's been given. So generate meta prompt, here it is, here's the method. This is our abstract problem definition, which we've seen before. It relates to handing off to a human operator, but this is the part that is the most important. Here we specify the prompt that we will send to the LLM algorithm. So we're stating that this is the your planning agent, you have to create meta prompt used to, and this is the abstract task that we've defined. So we used to decide whether to hand off the conversation to user, and then we provide more details. Meta prompt should break down the task into smaller subtasks, each having own prompt, that will be executed by dedicated agents, think step by step when breaking the task. So all those details, including a part where we ask the LLM to output the result adhering to a specified JSON schema, and here we put that schema. Why we need JSON schema? Because we need to have a formal response. We want to have it structured so that we can process it later on. So you can see that we want to have the plan broken down into subtasks that can be then delegated to separate agents. Each task will have name and prompt for its local execution, and we also want to have the final fusion task, that will gather all the feedback from all individual sub-problem executions and make the final decision. So it will be formatted in that way. Right? So this is the part where we generate the meta prompt. And once the meta prompt is created, what we do next is we call ChatGPT or OpenAI. We're using OpenAI API and we're calling GPT-4o. This goes to the LLM response. We retrieve the response in the JSON format, and then we process JSON format. So we load it using JSON library and extract all those subtasks, because in the next step shown over here, for each subtask we will be creating our task execution agents. So we will be dynamically creating task execution agent, providing it with a name which defines the subplan name, as well as supplying it with the subtask prompt. Right? So the subtask prompt is the instruction that the agent will use to call its own LLM, but using this specific prompt associated with resolving that part of the problem. Okay? So again, we've created the agent, we've initialized its thread, we've called perset method, letting the agent to see that there is a new task for it to resolve. And we've also added agents to the list because we need to know how many agents, or basically how many tasks we're expecting to be resolved. And also there's a final fusion task that we extract from the plan at that stage, and that we will use later on for fetching all the results. So we've initialized all our execution agents, task execution agents. They started working in parallel. Remember, these are threads, they're modeled as threads. So now the coordination agent is waiting for them to finish their execution. So it just probes every second whether the resulting queue on which all the partial results from those agents should be deposited is equal to the number of agents in the list, so the number of agents that were initialized. And when that happens, it is the second stage where, or actually here you can see it's a third stage, where we can initialize our last agent, final fusion task agent. We call him knowledge fusion agent, that will now gather all these partial results and make its own judgment. The way it makes its own judgment is, again, if we go to our knowledge fusion agent, if we go inside the class that defines the functioning of that agent, you can see that inside that agent we define specialized prompt, where we instruct the agent to use the scores from each reasoning result, so from each subtask execution provided by those subtask execution agents, and calculate the weighted average score to determine the final probability for handoff. So that agent will use that instruction as well as all the outputs from other agents that executed their subtasks, and will make the decision. And again, we ask him to adhere to a specific format, so it's much easier to extract the results. So this is the knowledge fusion agent, and multiple task execution agents. What they do is they resolve subtasks. So we prompt them to simply resolve things that were tasked and expected them to sort out. We pass those subtask prompts as a parameter of the much larger prompt, and again internally we execute the LLM with predefined prompt, same version of the model GPT-4o. We wait for a response, and once the response is generated, we put the response to the queue. We've omitted the second stage here, which is commented, where agents could also cooperate, because in that case I just tried to simplify the whole scenario, but bear in mind that you could also allow agents to share information and cooperate. In here, all those task execution agents just execute their own local subproblems, and then they just share it to the final knowledge fusion agent. And once that's done, the agent executes its own fusion process, evaluates whether the conversation should be handed off to the more skilled operator, human operator, and outputs it to the main code. Here is the part where we're waiting for the result from the coordination agent. When we see there's something in the result queue indicating that coordination agent has responded, we extract it, use the JSON library to retrieve all the attributes, and then use the print to show the result. So let's now execute it. So let's have a look at the whole process by running that snapshot. Remember, it's just a snapshot. We're at a certain stage of the conversation. We're fetching the context, predefined context, and we want to observe how the planning would look like. Okay, so as you can see, the whole planning has been already done, finished. So all the calls to agents have been completed. We've got the final result, but let's start from the top of the screen, where we first see that we send the context. So all the prefixed conversation we've had between the agent and the customer, it goes to the coordination agent. This is the prompt printed out, but what's most important, once it's sent to the LLM, the coordination agent receives the reasoning plan as a JSON, in a JSON format. So over here you can see how the meta prompt usage allowed the agent to break down, of course using LLM, the generic or abstract problem into sub-problems. So here we've got subtasks, and here we can see that the first subtask is identify issue complexity. It has a prompt, determine the complexity of the issue the customer is facing. Is this issue straightforward, or does it require in-depth troubleshooting? Another task is check for emotional cues, again associated with specific prompt that will be used to verify emotional cues. Next one is assess automation capability, review previous conversations, urgency and criticality analysis. So these are all subtasks. So the big problem of deciding whether to hand off to human operator is broken down into multiple local analyses. And then there's this final fusion task where we evaluate handoff probability. So using the data from subtasks, calculate the probability between 0 and 100 whether the customer's conversation should be handed off. Okay, so this is the output from the meta prompt. And now we're here looking at the logs. We're entering into the phase where we delegate those subtasks to individual agents. We start those agents and they underneath prepare their own specialized prompts, and they call in parallel their internal LLMs, so to speak, to get the results. Here we are getting the results. Okay, so the subtask reasoning output from the agent that was checking for emotional cues. The customer appears to be frustrated and confused. Another one, agent identify issue complexity. The issue is likely straightforward since logging issues with product A related to blank pages can often be resolved by restarting the computer. So because we've introduced in the main prompt one way of resolving that problem, now this agent is, or the LLM is identifying that it's not so complex because there is a solution and it should be straightforward for agent to solve it. And now there's another output from agent that was assessing automation capability. Yes, the current chatbot can assist with logon issues related to product A by instructing the user to restart. Okay, so these are the local outputs. And now, once they're all finished processing, we're moving to the agent. So we've got coordination results in Q5, all have been completed. Now the final knowledge fusion agent will evaluate handoff probability. So it will gather all those local results and calculate the final response. So at the very end we can see the results. Here the need for handoff to a human agent is moderate. Automated assistance can likely resolve the issue, but human intervention might be beneficial if the user remains frustrated after initial troubleshooting. And the reasoning final probability, so probability of handing off to human operator, is 60%. So this is how it works. And now we will move on to a more elaborate scenario or live scenario where we will incorporate this planning module into the live AI conversational agent. We'll start the conversation, we'll start talking to the agent, and that planning will be triggered in the background by the decision-making process of the agent every couple seconds. And based on the outcome of that probability, at some point in time when it exceeds predefined by us threshold, we will trigger the handoff procedure.
Hello, how can I help you?
Hi, I seem to be having a problem with one of your products.
Could you please specify which product you're experiencing the issue with? Product A or product B?
It's product B.
What specific problem are you experiencing with product B?
I completely don't know, and I'm fed up because I wasted so much time trying to resolve it.
I'm sorry to hear that. Could you please describe any issues or symptoms you're experiencing with product B? This will help us identify the problem and find a solution quicker.
Listen, I don't have time for this.
understand your frustration. Let me connect you to a skilled human operator who can assist you further.
Okay, I've just muted the conversation. You can see that the handoff probability now is set to 78. So in the background of our conversation, the agentic reasoner that was evaluating as the conversation was going on, the probability to hand off to the human operator started from 0 and, as you can see, ended up with 78%. We can also have a look at the last context messages, and in here you can see that we've injected the last message before the AI assistant suggested handoff. We've injected a system prompt indicating that the current handoff to skilled human operator, the probability of handoff is 64 out of 100, and we suggest user to escalate the call to skilled human operator. And we did so by measuring, as the conversation was taking place, the currently computed handoff probability, and if it exceeded 60, that's when that additional prompt was injected to the context, to the LLM, that in the end suggested to the user handing it off to an operator. So as you can see, this is how we can introduce agentic reasoner as one of the modules within our AI Conversational Assistant that works underneath, works in the background, and evaluates the probability of handing off based on the evolving conversation.
This is the end of the presentation, and here I wanted to summarize my observations related to the work with agentic reasoner. The good thing is that breaking down abstract problems is effective and provides us with greater control. Being able to see how a more abstract plan is broken down into smaller sub-problems, we're able to evaluate it. It's no longer a black box, and we can fine-tune it, modify it. And this is especially important because we've got a second observation, and it's a bad one. I could still observe that the LLM that was generating meta prompts was generating different plans every time when it was requested to provide a new plan. Okay, so that was leading to indeterministic results on the level of planning and the subtasks that it was proposing. And also what I've observed was that sometimes I was obtaining non-deterministic, unreliable scoring. And of course, these issues or challenges, should I say, could be addressed by more refined prompting or selection of specific plans. So we just select the best plan, we just use it as a template, but still we have to be careful. It doesn't work just out of the box, just by providing an abstract plan without our human-in-the-loop control. So this is where we go to the ugly part, where at the beginning I said that it would be great to declaratively define problems we want autonomous agents to resolve and have them do that. At the moment, I think we're somewhere in between. So we can declaratively define it, we can create necessary software modules to break it down, we can use agents to execute those subtasks, but we still need to be in the loop, we still need to be able to monitor it and fine-tune it. And of course, I'm not saying that it's not doable, but it requires an in-depth evaluation. And if we want to delegate this fine-tuning to agents, then we need to add additional mechanisms that will guarantee high reliability and accuracy. So for example, an agent, rather than just executing plan or building a plan from the meta prompt, it should also very carefully evaluate its own reasoning. we haven't been looking into this, but this is something that definitely would be very interesting to investigate and use as an additional mechanism to guarantee that we've got reliable and highly accurate results. Thank you very much for your time.